Hello, everyone. Welcome to today's webinar. I'm Linda Wang, Senior Editor at Chemical and Engineering News, and I will be moderating today's event. This webinar is titled Thermogravimetry, a powerful tool for determination of thermal stability and composition of polymers, and is being sponsored by Netch Analyzing and Testing. CNN works with sponsors to identify topics of interest and value to CNN's audience, and consistent with CNN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that CNN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the live webcast. The presentation today is being sponsored by Netch Analyzing and Testing, part of the Netch Group, a mid-sized family-owned German company engaging in the manufacture of machinery and instrumentation with worldwide production, sales, and service branches. During the presentation, we will hear from Gabrielle Kaiser, Head of Scientific and Technical Communications at Netch Analyzing and Testing. Dr. Kaiser joined Netch in 1991, where she became Head of Customer Training and Head of Applications Laboratory, working in thermal analysis for more than 20 years. She assumed her current position in 2012. I will now hand the presentation over to Dr. Kaiser.
Thank you very much, Linda, for the kind introduction. And welcome, ladies and gentlemen, to today's webinar. And it's a great pleasure for me to discuss with you in the following, let's say, 45 minutes, how thermal stability and the composition of polymers can be investigated by thermogravimetry. You have heard about my name already. It's Gabriele Kaiser, and I'm a chemist from education, and I have now about 25 years experience in thermal analysis. The company I'm coming from, you have also heard about from Linda already. It's Netch Analyzing and Testing, and Netch Analyzing and Testing is a part of the family-run Netch Group. And analyzing and testing is producing thermal analysis instruments for thermal physical properties testing, and also of calorimeters, of accelerating rate calorimeters, which are used for chemical safety testing, for example. Here is the agenda of my talk today. At first, we will hear something about the definition of thermogravimetry and about the functional principle of thermogravimetric instruments. We will look on thermal stability and oxidative stability, because these two terms are not meaning the same. We will have look on how to select suitable temperature programs for TGA tests and how to evaluate and interpret TGA curves. I will give you an example for how TGA can be used for quality control, and last but not least, we will have a closer look on long-term stability predictions by using thermogravimetry. But let's start with some basic information about thermogravimetry or thermogravimetric analysis. If we are looking on some standards, then we can find a definition there, what thermogravimetry means. And thermogravimetry is a technique in which mass changes are recorded during thermal treatment. So that means while the substance is subjected to a controlled temperature program. Additionally, also a specified atmosphere is around the sample. The mass changes can be positive or negative, so that means we can have mass loss or mass gain. And the corresponding instrument is called thermobalance. We have heard this, I guess, already. The abbreviation in this context are TGA for thermogravimetric analysis and TG for thermogravimetry, but TG is also sometimes used as a name of the instrument themselves. We have different types of balance systems on the market for thermogravimetric instruments or thermobalances. One is the classical hang-down system or bottom-loading balance principle, in other words, and this is a principle which was already used for thousands of years. Even the old Egypts have used them. Another type of balance system is a top-loading balance, what we know perhaps from daily life, from supermarkets, from households, etc. And the third balance system, or a third balance system, is a horizontal balance, what can be found from time to time in analytical systems. Net thermal balance systems are all working according to the top-loading principle. And here in the next slide, we can see two representatives of the net thermobalance line, specifically dedicated to polymer testing. On the right side, you see the so-called TG29F3 Tarsus. It's the working horse for polymer testing with a temperature range between room temperature and 1000 degrees C. On the left side, you see the TG29F1 Libra instrument. This is the premium instrument of this polymer testing series. And this has an upper temperature limit of 1100 degrees C. It has a robust ceramic furnace, and what is really brand new, it has an automatic sample changer for high sample throughput, because it has two trays in microplate format with up to 192 positions. But let's have at first a closer look on a TGA curve or TG curve itself. What we see here is a measurement carried out on polyethylene, and we see here in this graphic two curves, a black solid line which represents the mass change, the TG curve, and a green dashed dotted line which represents the first derivative. So that means it's the first derivation of the TG signal versus time. The polyethylene was heated in atmosphere, so that means in nitrogen in this case, and what we see is that we have a complete mass loss of 100%. And this mass loss step takes place between, let's say, 400 degrees C and about 520, 530 degrees C. In the derivation, which is also called the TG curve, we can see a peak, and the peak temperature is around 477 degrees C. And this is a characteristic value which is often used to characterize the mass loss effect. Additionally, we see another temperature, and this is the so-called extrapolated onset. This extrapolated onset is the intersection of two tangents. One tangent is drawn at the curve before the mass loss starts, and the other one is drawn through the inflection point. And here we have then a value of about 456 degrees C. The onset, what is also mentioned in the table below, this is a little bit more shifted to the left side. The main application areas for thermogravimetry you can see over here, and these are also the points we will talk about later on. Thermal stability, is connected also to pyrolysis studies because both things are carried out in inert atmosphere or under inert conditions. Contrary to it, we have oxidative stability, which works in oxygen or air atmosphere. We will talk about later on about compositional analysis, so that means to find out how many, what amount of what component is inside the compound. We can have purity investigation, for example. This means to find out the amount of residual solvents. We can also study interactions with the environment, or sometimes we can do simulation of manufacturing processes. And this will also be a topic of the talk later on. We can also do kinetic studies, kinetic evaluation of the decomposition behavior of a material. So let's start with thermal stability, oxidative stability, and also compositional analysis. And if we are looking to another standard, in this time ASTM E2550, then we see the following definition, that a material thermal stability can be investigated by determining the temperature at which the material starts to decompose or react and the extent of the corresponding mass change. So that means there are two quantities which are important. It's the temperature at which the material starts to decompose, and it's also the corresponding mass change. And on the other side, if nothing happens at all, then it's an indication of thermal stability. And how thermal stability is carried out practical, we can see here in this scheme. It's very often just a heating segment in inert conditions or under inert conditions. And for polymers, inert conditions mostly mean nitrogen atmosphere. Heating rate is, for example, in ASTM E1131 standard is recommended to be 10 Kelvin per minute, but of course it can also be another heating rate. Typical range of heating rate is between 5 and 20 Kelvin per minute, but most of the instruments on the market can also realize smaller or larger heating rates. It depends always on the sample properties and sometimes also on the number of materials, number of samples to be measured. In this slide and in this example, I will show you the difference between the thermal stability and the oxidative stability. We see here in green the thermal behavior of a SEBS PP sample. PP stands for polypropylene and SEBS stands for styrenic block polymer with the components styrene, ethylene, butylene, and styrene again. And if we heat this material in nitrogen atmosphere, then we get a decomposition which starts at about 300 degrees C and ends at about 500 and a little bit. The main peak in the DTG curve, so in the derivative, is at about 451 degrees C. But if we do the same experiment in air, then we get a completely different picture. And this is what you see here in blue. The decomposition starts earlier, and also the decomposition profile is different. The main DTG peak is shifted to about 355 degrees C, so that means almost 100 Kelvin earlier. sometimes it's so that the characteristic temperature profiles or the characteristic decomposition profiles can also be used to identify a polymer. And this is, for example, possible here if we compare, for example, here polymethyl methacrylate, PMMA, in green with polypropylene in black, polyethylene, low-density polyethylene in blue, and polytetrafluoroethylene in red, then we see that the decomposition is changing in temperature. The first one, the green one, decomposes at a much earlier temperature compared, for example, to the polyethylene or to the PTFE. Unfortunately, this is not always the case. In some cases, the decomposition temperature is not specific enough for differentiation and thus also for identification. Later on, we see an example for it, and I also will tell you how we can find, nevertheless, a way out. Let's go over to compositional analysis, and let's have again a look inside of a standard, and this time again ASTM E1131. And this standard says that thermogravimetry is suitable to determine the amount of polymer inside of a compound, but it's not limited to that. We can also determine the amount of volatile matter, for example, plasticizer, the amount of combustible material. This can be, for example, added carbon black, and ash content. And ash content is mostly the filler, what is inside of the material. Here we have an example of it, and this is again a polyethylene measurement, but it's not pure polyethylene, and this we can see on the mass loss step with 98.3% roughly. If we remember what we have seen before, that polyethylene decomposes in nitrogen atmosphere or under inert conditions completely, and here we see this is not the case. We have still a certain residue, and this residue we can combust or burn off in air atmosphere. So that means the temperature profile in this case was heating up to 850 degrees C in nitrogen atmosphere, and then we switched over from nitrogen atmosphere to air atmosphere, and we were going up further to almost 1000 degrees C. And in the air phase, so that means in the oxidizing phase, we see another small mass loss of about 1.7%. And this is due to added carbon black. But sometimes it's so that we don't have always base polymers which are decomposing completely in nitrogen atmosphere, but sometimes we also have base polymers which form so-called pyrolytic carbon. So that means that they don't decompose completely. And the question is now, is it possible to separate the amount of such pyrolytic carbon from added carbon black? And it is possible, but for doing this we have to modify the temperature program a little bit. And such a modified temperature program you can see here on this slide, and here we go up at first in the first heating step up to 600 degrees C in nitrogen atmosphere, then we cool down a little bit again down to 400 or 300 degrees C and keep this temperature constant for a while, everything still in nitrogen, and then we switch over to air or oxygen, so that means to oxidizing conditions for combustion. And if we do like this, then we can see in the final oxidizing step, we can see two mass losses. In this case, one of about 1.7 and something percentage, and a second one of about 1.2%. If we use such a temperature profile, then the decomposition of the polymer, here it's NBR, does not take place completely. There's a certain amount of pyrolytic carbon formed. This pyrolytic carbon has smaller particles, a higher surface, and thus also a higher reactivity than the added carbon black, and therefore we can relate the first step to the content of the pyrolytic carbon and the second step to the content of the added carbon black. Another situation is if we have, let's say, a rubber mixture and we have a high boiling plasticizer inside. High boiling plasticizer means that the evaporation of the plasticizer and the decomposition temperature of the polymer or the polymer mixture is quite close together, and it's sometimes difficult to separate them. A possibility to make the situation a little bit better is to use reduced pressure inside of the thermobalance, and this is given here in this graphic. So that means the reduced pressure, or how we called it here, vacuum, leads to a boiling point depression of the plasticizer, and therefore, as a consequence, the plasticizer content can be well separated from the decomposition of the polymer. After the polymer decomposition, the system was refilled with nitrogen in this case, and then after a while the atmosphere was changed again to oxygen. We have seen now different temperature programs or different temperature profiles for analyzing polymers, and now the question is how to select a suitable temperature program for a thermogravimetric test. And this is a question where the Proteus software can help, and especially the Smartmode interface of the Proteus software. Here on this slide you can see a part of the Smartmode interface, and you can see several buttons. You can read wizards. These are some templates for temperature profiles. You can read user methods. These are really is a part where the operator can create its own methods, and you can also find predefined methods, and these are measurement methods which are coming already with the software itself. And I will show you now how such a predefined method can look like. For example, the task is to make a measurement according to a certain standard. Let's say according to ASTM D6370, and this is the compositional analysis of a rubber sample by thermogravimetry. And if this is our task, then we have just to click on this predefined method, and what we see as a consequence is such a window where the necessary temperature program is already predefined, and we have just to add the substance, the material, the sample-specific information before we can start the whole thing. But of course, if we don't want to use such a predefined method, we can also make our own temperature program. For example, by using wizards. And here on this list, you can see several wizards which are available. And if we think back to the example where we have separated the amount of added carbon black from the amount of pyrolytic carbon, then we had a special temperature program, heating, cooling, isothermal heating, and the second heating step was under air or under oxidizing conditions. And if we do this here, for example, then we call up the appropriate wizard, and we get a picture like this. So that means here again we have to add the material specific information, but for programming the measurement, we just have to give in the starting temperature, the ending temperature, the heating rate, and the length of the isothermal segment. But it's not necessary to build up the temperature program step by step. Let's go over to the evaluation and the interpretation of TGA curves. And the first thing what I would like to present you is an ideal curve where we can see two steps. And the mass change, of course, is evaluated from the step height. And there are several interesting temperatures for characterizing the mass step, the mass loss step, the extrapolated onset temperature. We have seen it already. A similar temperature we can also evaluate at the end of the step as extrapolated end temperature, and the midpoint, what is in this case the inflection point of the step. The midpoint or the inflection point is identical to the peak temperature of the first derivative, and this is a temperature what we have seen already several times, and this is very often used as a characteristic value for characterizing the thermogravimetric effect. But the derivative is also used very often additionally for finding the right limits for the step height evaluation, because we have to define where to start and where to end the step height calculation. In this case here, it's an ideal curve. It doesn't matter if we start a little bit more to the left side or a little bit more to the right side. But in real cases, this is often different, and we have to find the right position. And to find the right position, one possibility is to check the maximum between two DTG peaks. And here, this is a real live curve, and indeed there is the shape is a little bit different to what we have seen before. There are some regions inside of the curve which are not ideal, some overlapping effects which are not clearly separated from each other. And the question is now how to evaluate such a curve. And one possibility, what we have over here and what the NETCH Proteus software offers, is the auto-evaluation functionality. Auto-evaluation means it's an intelligent mathematical algorithm behind what automatically evaluates the curve. It's not necessary to set any evaluation limits. It's not necessary to create any evaluation macro before. We just have to highlight the curve and to click on the corresponding icon, on the auto evaluation icon, and then we will get a result like what we see on the next slide. So that means a result like this. And if we are using the same curve, then we also will get always the same result by using auto evaluation, independent from the operator. So it's a real user independent result. Experienced operators can use this auto evaluation as a second opinion, for example. Sometimes the task is also to find out or to get an idea about the polymer we are working with, especially if it's a new material, if we have never measured the sample before. Such curve as is displayed here in blue. What kind of polymer, which kind of polymer could this be? To find this out, one possibility is to use the curve comparison database Identify, which is also a part of the NETS Proteo software. And to use this Identify database is again only necessary to highlight the curve and to click on the corresponding icon. And then we get something what perhaps we know already from spectroscopic instruments like FTIR or something like that. We can make a library search. And the experimental curve will be compared with curves stored already in libraries. And then we can get a result as what we see here, for example. We get a similarity of more than 98%, a similarity of more than 98% for the HNBR curve, which is stored already in the library. And the blue curve, what is presented on the graphic, this is the experimental one, and the pink one, this is the library curve. And we see also just by looking on it that they are very similar. Some slides before, I told you already that unfortunately not all decomposition profiles are specific enough for polymer identification. And this is an example which symbolizes it, which shows this situation. We have here two curves, a blue one and a red one. One comes from the measurement of PA6, so polyamide 6, and the other one is derived from a measurement from polyamide 6,6. But from this curve itself, or from these curves itself, it's not possible to say which curve belongs to which material. Is the red curve polyamide 6,6 or is it polyamide 6? Nobody knows. But here we have also a possibility to get some further information, and this further information is CDTA, which stands for Calculated DTA Signal, and this means that the sample thermocouple must be in a close contact to the sample crucible to feel any temperature change inside of the sample. And then it's possible to calculate such a CDTA signal for getting more information. And if we do this here in our case, then we get two peaks. A blue one with a peak temperature of 223 degrees C, and a red one with a peak temperature of 262 degrees C. And now we can separate them. Now we can say that the blue one is PA6 and the red one is PA66, because these temperatures, what we see here, are the typical melting temperatures of these materials, or lying in the typical melting range of these materials. I promised you to show you also an example how TGA can be used for quality control purpose, and this is what I will show you now. Let's say we have any kind of recycling material represented by the black curves here. This is the TG profile with a main mass loss around between 350 and 500 degrees C. The corresponding DTG peak is at about 456 degrees C. And first step is to find out what kind of polymer it is, and you know already that we can use the identity functionality for this purpose, and if we do so, then we see that we get a very good correlation to a reference curve of PA6 with 30% glass fiber content. The temperature position is very similar, only the filler content is a little bit different. What else can we do with identify? We can create a class. What you have seen before, or what we have seen before, was always a one-to-one comparison. That means a comparison of a just measured curve with a certain curve which was stored already in the identified database. But we can also make comparison with classes, and this means we can make a comparison of an actual curve with the average curve of a set of measurements. And such a class must be created at first, needs to be created at first. And for example, here we have several measurements of the same material to create such a class, and the class, for example, can be named as PA6GF, so polyamide 6 with some glass fiber inside. And then in the second step, I can take a new measurement, a new material, a new lot, and I can try to find out if this curve, if this material belongs to the class I have created before or not. And if I do so, and for example, I concentrate at first on the polymer itself and also on the polymer decomposition, what you see here in the temperature range between 260 and 540 degrees C, then we get a similarity of more than 90%. It's about 98%. That means that the base polymer is really the same. It's also polyamide 6 with some filler inside. But if I don't concentrate on the polymer decomposition, if I use the entire curve and compare it to the glass, with the glass, then I can see, or we can see, that the similarity goes dramatically down. It's much less than 90%. It's about 66%, and this is especially due to the fact that we have an additional small step above 600 degrees C. Let's go over to the last example I would like to show you today, and this is the prediction of the long-term stability of an electrical insulation material by thermokinetic analysis. NETCH does not offer only instrument software, so the NETCH Proteo software, what you have heard about already, but NETCH offers also thermokinetic software for further evaluation of the thermoanalytical data. And the task of this evaluation was to find a time interval after that 10% of the organic matter of an electrical insulation material was decomposed. And for doing this, we made several measurements on this electrical insulation material, and you see here some of the dynamic measurements with various heating rates. From 0.5 Kelvin per minute, this is the light green curve, up to 10 Kelvin per minute, this is the red curve. And what we see is that we have a shift of the effects of the curves to higher values with increasing heating rate. The profile of the measurement curve, the profiles of the measurement curves is more or less the same, so it's not changing much. And the mass loss, the total mass loss, is also more or less the same. The organic content is about 33%. But if we are intending to make predictions, long-term predictions, it's always advantageous to have not only dynamic measurements, but to have also some isothermal measurements included. And two of the isothermal measurements you can see here. It's an isothermal measurement at 200 degrees C, this is the light blue curve, and at 250 degrees C, it's the dark blue curve. And if we are looking on the time scale, we have more than 500 minutes, and within this time we have in the light blue case about 0.6, 0.7% mass loss, and in the dark blue case about 2%. And the task for the kinetic evaluation is now to find a model which describes all these experimental curves as good as possible. And the result of such a kinetic evaluation you can see here, for example. The colored symbols are the original measured data, and the black curves are the calculated curves based on the model what we see on the right side. So the best model what was found was from A to B and B to C, but this was also branched from B to D and from D to E. So this is a formal kinetics approach, and behind such reaction from A to B, different mechanisms can be found. But with this model, it was possible to get a really good fitting. And based on this model, then it was also possible to make some prediction, and the prediction is seen over here. The question was about 10% decomposition of organic matter. We have seen that the total mass loss of organic matter was about 33%, so that means 10% is 3.3%. And now the evaluation is, or the question is, how long does it take until 3.3% mass change are reached during isothermal storage at a certain temperature. A side condition was that this time interval should be longer than 20,000 hours. And our prediction showed that it was possible, or it is possible, with a storage temperature of 170 degrees C, then we get 66,000 hours as a result. But if we just go 5 degrees C higher, then this time interval is reduced to about 17,000 hours. Yeah, let's sum up what we have heard in this webinar. We got some information about thermogravimetry or thermogravimetric analysis, that we measure here mass changes as a function of time or temperature. We saw the difference between the terms thermal stability and oxidative stability. Thermal stability is always carried out under inert conditions, and oxidative stability in air or oxygen atmosphere. We saw that it's possible to select suitable temperature programs for TGA tests in an easy way by using the Smartmode interface of the NetProteo software. And also auto-evaluation and identify can be of great help to get user-independent and reliable results. And additionally, we saw that the Net Thermokinetic software is an additional software tool for further evaluation of the thermoanalytical data and to get even more information about the sample properties. I hope you could find something interesting within this webinar, and I can just thank you for your attention.
Thank you, Dr. Kaiser, for your terrific presentation. Now begins the Q&A portion of this webinar. The first question I have here is, if curves overlap, can you separate the curves by repeating the experiment by heating at a slower rate? Is this too simplistic?
It depends a little bit on the kinetics of the processes which are going on. Sometimes it's possible to that an overlapping can be, or let's say in other words, that the resolution of overlap peaks can become better if lower heating rates are used. But in some cases it's also the opposite. So that means that a higher heating rate leads to a better separation. So therefore it's always a little bit trial and error to find the correct or suitable heating rate for a certain investigation.
Okay, thank you. Another question I have here is, I work on mineralizing inorganic metal, for example, gold inside a protein shell. Can I detect the percent content of gold using TGA? How much minimum protein mass will I need to detect?
Is the gold, what is in? Is it? Did I understand it right that it's gold inside of a protein?
Well, so it says, I work on mineralizing inorganic metal, and in parentheses it says, for example, gold, and then in parentheses, inside protein shell. Can I detect the percent content of gold using TGA? How much minimum protein mass will I need to detect?
What also can be perhaps is, and I'm not sure if I got it right, if the matrix around the gold is not an inorganic one, if it's an organic one, then perhaps it's possible to burn off the organic matrix, and so that the residue is still there, and this is the gold content. But perhaps we should discuss this question later on in more detail.
Okay. Another question is, aren't these specific values going to be dependent on the heat rate?
What kind of specific values?
That I'm not clear.
So if it's the temperature value, then it's dependent on the heating rate. So as you have seen in the slide, which was representing the dynamic measurements for the kinetics evaluation. So let me go back. So this one here, you see that you really have a shift in temperature with increasing heating rate. So that means the higher the heating rate, the more the temperatures here, for example, the extrapolated onset temperature, and of course also the peak temperature of the DTG curve, which is not presented here, is shifted to the right side. Mm-hmm. Therefore, and this is always the case for thermoanalytical measurements, it's quite good to have always comparable conditions if one material should be compared to another one.
Okay, great. This question, is TGA and CDTA performed in the same instrument?
TGA and DTA.
TGA, uh-huh.
DTA and DTA, or?
TGA and CDTA.
CDTA. Oh, sorry, I didn't understand it well. Yes, of course. Of course, this is performed in the same instrument, because the CDTA signal is a calculated one, and it's calculated based on the sample temperature, which is measured by the sample thermocouple. And the sample thermocouple, for example, is part of the sample holder. Let me just go back to the here. This is, I don't know if all of you can see now the picture, the slide on the screen. In the left part, there is a presentation of the sample holder, and if you look closer to it, then you can see small wires, and these small wires are representing the thermocouple, and this thermocouple is measuring the temperature, the sample temperature. And if the sample thermocouple is close enough in contact with the crucible, then it can detect any temperature changes inside of the sample. And this signal is then compared to the program temperature, and the difference between these two values are used to calculate the CDTA signal. And this is represented here as a scheme in the right part of the slide, of the picture.
Okay, thanks. This question is the identify functionality only limited to libraries which are part of the instrument software, or is it possible to create user-owned libraries?
Each user can create its own libraries, so it's also very easy to do that. The measurements have just to be loaded, and then there is a possibility to include it directly into the identified database. Each user can also define the name of the library, and it's also possible to create classes, what we have seen already. But of course, it's also so that if the software comes, or when the software is installed at the instrument, there are some library entries already there. But each user can create its own libraries, and it can also extend and edit the libraries at any time.
Okay, thanks. I think we only have time for maybe two more questions here. Can you comment on relative advantages, disadvantages using alumina versus platinum TGA pans?
Alumina versus platinum. Did I understand it right? Alumina versus platinum.
Yes, correct.
So it depends always a little bit on the sample properties. So this is a common aspect, that samples should not react with the crucibles they are put inside. And you, for example, if you have some material which will melt during heating, then perhaps it can react with the crucible, and this should be avoided. So therefore, metal melting in metal crucibles should be avoided, for example. Or this is one aspect. Another aspect is that also sometimes platinum can have catalytic effects. This is also possible. So, and influence the thermal behavior of the samples inside. Another thing is that alumina has a smaller thermal conductivity. This can have perhaps an influence if somebody is working with high heating rates. This can also have an influence, but the main point is really the compatibility between sample and crucible material. If somebody is working with polymers, for example, then in principle it doesn't matter in most cases. Just for silicons, for example, it can perhaps have an influence, but for most of the polymers, or for many polymer samples, it doesn't matter if alumina crucibles or platinum crucibles are used. Another thing what I'm just remembering is the size of the crucible. For a measurement, the ideal case is to have a representative sample. And if the sample is quite inhomogeneous and a larger crucible is necessary to make the measurement, to make a proper measurement, then often it's so that alumina crucibles are available in larger sizes than platinum crucibles.
Okay, thank you. Unfortunately, we're getting close to the end of this webinar, so I'm afraid that's all the time that we have. Thank you again, Dr. Kaiser, for your fascinating presentation, and thank you, participants, for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Thank you, On24, for technology and production services, and thank you to Niche Analyzing and Testing for the sponsorship that made this interactive webcast possible. For CNN webinars, I'm Linda Wang. Goodbye.